Hello everyone, I'm J Wildberger. Thanks for joining me. This is a new series on classical and quantum mathematics. We might even say classical versus quantum maths because there's a bit of a tension or a bit of a dichotomy between the mathematics associated maybe more with classical physics and with 20th century quantum mechanics. Now, quantum mechanics is really a remarkable development. It really ranks up there with the 17th century introduction of Newtonian mechanics as sort of a pivotal point in the history of physics. And it happened in the first half of the 20th century, but its influence is still very much with us today, and it really explains so many aspects of modern technology and chemistry and modern life. But there's undeniably a mysterious, strongly confusing aspect to it, because it appears that what's going on at the quantum level is so completely different and unusual and almost incomprehensible to us. And so there's still a lot of debate in physics circles as to the meaning of quantum mechanics, if indeed that even makes sense. So I'm interested in that, and I'm interested in that question. But as a pure mathematician, I'm also interested in how that challenge of understanding quantum physics relates or connects with mathematics. So it turns out that there's a lot of ways in which this dichotomy between classical and quantum physics is reflected in the mathematical world. So I'm proposing to try to explore this range of topics and maybe try to get at the physics from a mathematical point of view. So trying to shed some light on what's going on, starting with purely the mathematics. So we can think of mathematics as a potential laboratory in which we might think about some of these physical ideas. So let's start out with a brief description of some of the differences between the classical world and the quantum world, starting originally from physics, but we can see that a lot of these distinctions are also somehow manifest in the mathematical world. So classical, somehow connected with continuous phenomena, quantum more associated with discrete phenomena. Commutative, classical mathematics typically grounded in commutative mathematics, quantum physics in non-commutative mathematics. There's an exactness to the classical world which is lost in the quantum world, becomes more approximate. And correspondingly, there's a predictable aspect to classical thinking which becomes more probabilistic in the quantum world. In classical physics, we concern ourselves with little particles and Newton's laws, while in quantum physics, waves start to play at least an equal role in the description of things. There's some sense in which we're going from finite dimensional stories to infinite dimensional stories, and going from local things to non-local things. So especially having to do, say, with entanglement of particles over vast distances. And there's this almost philosophical role of the observer and the measurement problem, and what effect does observation have on the story? In classical physics, classical mathematics, the observer is maybe part of the story, but you can sort of identify or separate the role of the observer from what's actually being observed. Not so easily in quantum mathematics or quantum physics anyway. So can we understand quantum mechanics? Well, that's a big challenge. Feynman, I think, famously said, that nobody basically understands quantum mechanics. And I think that situation hasn't changed all that much over the decades. There are actually quite a wide range of opinions that the physicists have about the meaning of quantum mechanics. And there's also, widely different views as to what's really going on there. But I'm not necessarily wanting to come to some definite conclusion about that. I think that might be too ambitious, although we might aim towards that. But I'm sort of interested in the mathematical side of this entire story. So I believe that there is a mathematical side to the physical world of quantum mechanics, and that it manifests itself in all kinds of interesting ways, and that there's really a very powerful potential for putting some of these things together and trying to get an overview of quantum mechanics from a mathematical point of view. Which is not to say that we're going to go start doing physics and looking at the mathematics involved in the physics. Rather, I want to look at those aspects of mathematics, pure mathematics, which ultimately have a strong sort of quantum aspect to them. And I want to investigate those things and try to understand them more deeply and more carefully. And maybe, or maybe not, but maybe that will shed some light on the physics as well. So I claim that in fact, there is a quantum side to mathematics, and that it's actually logically independent of modern physics. You see that it's rather an interesting kind of coincidence that in the 1920s and 1930s, when quantum mechanics in its somewhat modern form was really being developed in this remarkable burst of brilliance due to quite a lot of people. Correspondingly, pretty well at the same time, there were some really important investigations being made in pure mathematics in the direction of Lie groups and Lie algebras and representations associated to names like Élie Cartan and Hermann Weyl, and sort of spectacularly culminating in Weyl's character formula for compact simple Lie groups. And it turns out, after the fact, like decades later, we started to realize that Weyl's theory, in some sense, could be reframed to make it very close, or having a lot of parallels with this sort of transition from classical mechanics to quantum mechanics that was sort of being developed at the same time as Weyl was working on this pure mathematics side. Weyl's a very interesting character in this story because he actually plays an important role in the development and the understanding, the mathematical side of quantum mechanics. So he has his feet in both camps, and we'll have to talk about Hermann Weyl. But anyway, I'm sort of interested in this sort of coincidence, and for me, it's at least theoretically possible that it could have been, if history had been slightly different, that we could have sort of discovered quantum mechanics from a mathematical point of view quite earlier and independently of the physicists. So that could have happened. And so it's interesting to think about, the logical structure. Mathematics is not necessarily just a tool that the physicists are using. It can also, in fact, be a separate laboratory for exploring issues which are directly related to this physics, but have a completely independent existence in the world of pure mathematics. And that's what we're interested in this series. So what are some of these mathematical areas that are pretty close to quantum theory? Well, here's a rough list of them, and probably I could come up with some more, and maybe we will come up with some more during the course of these investigations. But first one is the theory of symplectic manifolds. This is geometry, and associated Lagrangian and Hamiltonian formulations of Newtonian mechanics. In what's also sort of a remarkable coincidence, so Newton developed his laws of motion using his newborn calculus in the 17th century, and then eventually, like 100 years later, Lagrange came around. Euler also contributed and sort of reformulated Newton's laws, now called the Lagrangian point of view, based on principle of least action, which turns out also to be really crucial for modern physics. And then Hamilton later on came around and gave another kind of reformulation, which probably Lagrange had already sort of put his finger on in some sense. But it turns out that when quantum mechanics then arose in the 20th century, in the first part of the 20th century, that these reformulations of Newton's mechanics were just exactly somehow what the physicists needed. They were the sort of mathematical tools that they could then use to try to formulate what's going on in quantum mechanics. So there's a sense in which there's already a sort of a coincidence here at this level, quite a bit earlier before real quantum mechanics developed. There's entire areas of modern analysis having to do with operators, operator algebras, Hilbert spaces, spectral theory, okay, that are very close to quantum mechanics, indeed are important tools for certain approaches to quantum mechanics, but also I think quantum mechanics sort of naturally has something to say about them. There's Q series, which is a branch of algebra or / number theory or / combinatorics, which often also has a sort of a quantum aspect. There's some sense in which information theory, as developed by Claude Shannon, also is an approach which these days is some people considered a very important way of thinking about, a possible way of thinking about quantum mechanics. For me, this one here is very prominent and important. I've mentioned it already, the representation theory of Lie groups and Lie algebras, which is a huge subject which just exploded in the 20th century, and partially at least because of these newfound strong connections with physics and indeed quantum mechanics, but also with relativity. So this is a very important topic even for the theoretical physicists these days. They have to become quite conversant with this topic. And very interestingly, this is going back again to Weil, very interestingly, there's aspects of quantum mechanics that are appearing in this theory completely independently of any physics. And I think that's not well enough appreciated, and it's something I would like to talk about and try to explain. There's a theory of quantum groups, okay, which obviously has some connection with issues of quantization. Of course, probability theory, measure theory, because quantum mechanics is in some sense inherently probabilistic. There's Fourier analysis. There's a sort of corresponding uncertainty principle in the Fourier theory world, which sort of reflects or is a mathematical version of the Heisenberg uncertainty principle. There is something called geometric quantization, associated with names of Kirillov and Constant and other people. Then there's another sort of geometrical theory having to do with moment maps and sort of a reverse arrow from quantization called dequantization that I've had some occasion to think about. So in fact, in some sense, I've been thinking about these kinds of things for a long time because my PhD thesis, which I did at Yale University under the supervision of Roger Howe, that was many years ago, 40 years ago probably or so. The title of that was Quantization and Harmonic Analysis on Nilpotent Lie groups. So already at that early time, I was quite interested in quantization. So it's been a kind of a recurring thing. Every so often I think, I'd like to think more about quantum mechanics and try to understand what's going on there, especially the connections with mathematics. So these are some of the areas that we will try to explore. And I will try to give you some kind of, introduction to these things, even though some of them are quite sophisticated. But I'm going to try to do that in a way which is also consistent with my general philosophy of avoiding infinite things and avoiding axiomatics and set theory and indeed a lot of the limiting processes of analysis. So I have to find alternate ways of stating what's going on with these things. And I hope to do that also to promote the idea that it is possible to look at important parts of mathematics, that are important in physics, not necessarily with the usual status quo belief system that's currently wedded onto the education of most mathematicians these days. Now, my thinking is that this series is also going to overlap and complement some of the other series that I currently have going, such as the exceptional structures and dynamics on graphs, which is available for members on the Wild Egg channel, which is also the main place where this series is going to be. So it's primarily for members of the Wild Egg Mathematics Courses YouTube channel. There's also a series called Diffusion Symmetry. We're talking about hypergroups, okay, which is at the Insights into Mathematics YouTube channel. There's another members series called Explorations with Q series. So that's also in the Wild Egg. And there's obviously going to be connections here. And there's also another intended series that I'm hoping to eventually start, where I want to sort of squarely deal with the representation theory of Lie algebras and Lie groups sort of as a separate topic, which is a huge thing. But I think it's well worth trying to give an exposition of that in what I consider sort of relatively simple-minded, accessible terms. So I'm hoping that there will be resonances here and that some of the things that you're going to be exposed to in this series will overlap maybe, or at least resonate with some of the things that you're learning about in these other series. So there's a lot to do here, lots of interesting things to learn. So in the rest of the video, I want to attempt a very brief and cursory sort of overview of the historical aspects of the development of quantum mechanics in the physical world. So this is a really interesting story with, that requires huge explanation. But I'm just going to give you an overview just sort of to position us. The physics is not really my main aim, at least in terms of exposition. I want to explain the corresponding mathematics, which is sort of adjacent to the physics, but having at least some cursory understanding of the physics and the issues involved there is going to be necessary to orient us. So the story of quantum mechanics really begins pretty well exactly in the year 1900 with the work of Max Planck. But before that, we have to understand that 19th century physics had these very big successes, and physicists at that time were very confident that they more or less had a grip on the nature of reality, that there were some things still to be figured out, but more or less the basic edifice was there. And it was really based on perhaps three things: the Newtonian laws of mechanics that we've already talked about, along with the reformulations of Lagrange and Hamilton. And then there was Maxwell's laws of electromagnetism, having to do with light, electric fields, magnetic fields, etc. And there was also a theory of thermodynamics that had been developed, Clausius, Boltzmann, and others. So there was now a second law of thermodynamics, a very important law. So these things sort of provided a theoretical structure. But it turned out that the 20th century would see all these revolutions in thinking, many of them associated ultimately with Albert Einstein, special theory of relativity, general theory of relativity, but he was also a contributor to quantum mechanics. But, sort of basically all bets were off in the 20th century. Things just became hugely more complicated and weird and strange. And the certainty that the 19th century physicists had to be let go of. Okay, so the story probably starts with Max Planck, in his study of black body radiation. And this is around the year 1900. So the story is we have some box, which is sort of at some uniform temperature, so it's a black box. And inside there's some gas, which is, at the same temperature as this thing. And we have a little hole, so this thing is emitting radiation, so we can see how hot it is. So see, what color. It's hot in there. Maybe there's a red coming out. So if we actually look at the frequencies of light coming out, well, there's a range of frequencies. Okay, and the range of frequencies, the intensity of the light for different frequencies turns out to have some graph that looks like this. And that's not really something that was predicted by the current theory. So it was a bit of a struggle to figure out, what's the shape of this thing here and why is it this way. And that's what Planck did. He found an equation for this thing, in terms of the frequency f, frequency of the light being emitted or the radiation being emitted, the intensity I, and then there were two constants that end up playing a huge role in this entire story. Planck's constant h, which is some really small quantity in traditional units, and Boltzmann's constant coming from thermodynamics. And it's that this curve is given by 2hf cubed over exp of hf over kt minus 1, where temperature is T. So the whole curve depends on T. Now, in his analysis of this and obtaining this equation, Planck had to make some rather unusual kind of postulates. He had to rethink things. And eventually he came to this really fundamental realization that the energy of light, was in some sense sort of quantized. So this is the original meaning of quanta, meaning sort of some small quantity of which integer multiples end up figuring. So there's not an infinite divisibility like we might think. So he found that the energy was not in a continuous spectrum. It rather had discrete values, and that those discrete values could be in terms of sort of some fundamental energy, which was given by hf. H is this constant, f is the frequency. So this was sort of the original quanta of that started quantum mechanics, and and that was really quite a remarkable remarkable formula and remarkable thinking that light had this different property than people had thought previously. The next important contribution was by Albert Einstein. In 1905, a paper on the photoelectric effect, which ultimately gave him the Nobel Prize, although 1905 was also the year of special relativity. And in fact, another paper, this was like a super year in the history of physics. And Einstein was looking at trying to explain a certain effect called the photoelectric effect. We have some body with some electrons here, and you shine light on this thing, okay? And that sort of dislodges the electrons, and then you have some voltage potential here, and you detect these electrons after they've emerged from this voltage separation. So the voltage that you have here kind of allows you to determine the energy of the electrons coming out. So you would think that if you turned up the intensity of the light, okay, it's brighter, okay, that's more, it's hotter, there's more energy coming out of this light on this light beam. You would think that that would then increase the energy of the electrons that are being emitted from this in this photoelectric effect. But that's not what turns out to happen. It turns out that the energies are all sort of dependent really more on the frequency of the light rather than the intensity of it. Okay? In fact, here is Planck's relation again, E equals hf. It's this E, the energy associated with the frequency f, that's contributing to the energy that the electrons are emitted. So Einstein's explanation of this was very novel. Okay, so people had understood light as a wave in terms of Maxwell's electromagnetic theory, and they were very comfortable with the wave mechanics of light in that context. But Einstein realized that there was some aspect here in this situation which suggested that light actually had a particle nature as well as a wave nature. And so, see, what he's saying is that, the light can be viewed as actually having sort of a particle nature. So these little particles of light, called these days photons, and the photon is coming down here, and an individual photon, which has a certain frequency, just like depending on the color of the light, will have a certain energy. That's the whole point of the Planck law, that the frequency determines the energy of this photon. And it's that single photon hitting a single electron and dislodging the electron, sort of bumping it out, that generates this electron movement. And so that the energy transfer from the photon to the electron is exactly of this amount. That means if you shine more light on the story, what you're doing is you're shining more photons. There's now a lot more photons, but they all still have the same frequency. And that means that you're going to have more electrons being emitted, but the actual energy is not going to be increased. It's still going to be just dependent on the frequency of the incoming photon. So this led Einstein to this remarkable postulate that light, even though it obviously has a wave-like aspect, that it also has a particle aspect, and that these photons, directly carry Planck's relation in terms of their energy. So this work of Einstein was not taken on board for quite some time. It took people many years before they started to realize that Einstein actually was right here. And that also provided important confirmation for Planck's law. Another really important development in sort of the earlier quantum theory. So quantum theory sort of has two parts. There's the earlier quantum theory up to about mid-1920s, and then the later development. And the other sort of really important development in the earlier part is the atomic model of the atom. That's largely due to Niels Bohr, working on modifications of previous theories due to Thomson and Rutherford. So his model of an atom, say the hydrogen atom, which is the simplest one, you just have a single small nucleus and one electron zipping around. It was very much like a planetary kind of story, where you have a nucleus like playing the role of the sun, and you have the electron playing the role of a planet and it's going around. And he, sort of adopted these points of view of Planck and Einstein to assert that these the shells or the orbits on which these electrons are going around are discrete, and they are constrained in energy by that their energies have to be just integral multiples of this basic thing. And so that ended up having the consequence that electrons actually end up in certain specific shells. So if you have larger atoms with more electrons and bigger nuclei, then the electrons end up organizing themselves in little shells, okay? And the inner shell has room for 2 electrons. And then the next shell has room for 8 electrons. The next shell room for 18 electrons, and so on. And the pattern is that if you divide all these by 2, you get 1, 4, 9, 16, you get the square numbers. So there's a nice sort of relationship between sort of this quantum number and the number of electrons in one of these orbits. And also he had a nice geometrical interpretation of the various radii of these shells. So this was, I mean, ultimately this model had to be modified or abandoned to a certain extent with the newer quantum theory, but this was still a very compelling model because it allowed one to explain all kinds of aspects of the chemical periodic table in terms of the properties of various elements, in terms of the configurations of the electrons, and you know, whether the shells are full or not. You know, if a shell is completely full of electrons and there aren't any sort of extra electrons around in the next shell, then that's a kind of an inert, relatively stable element, like an inert gas, etc. So this was a very important kind of model, even though ultimately it was superseded mechanics. And then in the 1920s, all kinds of new developments took place, and the whole subject was elevated to a much more serious level. And a lot of really very smart people made remarkable contributions here, so it was like a golden time for physics. And so very briefly, I'm just going to mention some things, and you know, in the course of this series, maybe I'll be able to talk a little bit more about some of these things. So Wolfgang Pauli discovered something called an exclusion principle, also sort of related to the spin of an electron. So it turns out an electron has some internal kind of spinning also. And this allowed him to somehow sort of partly explain what was going on with Bohr's model of the atom. You know, the reason why these shells couldn't support more than those number of electrons that we talked about, because there was some principle that different particles had to, of this kind, had to sort of be in different states, okay? Louis de Broglie, who was a French, actually I think a prince, okay, some royalty in France. He also became physics royalty because he really took this particle wave duality that was sort of, you know, initiated perhaps by Einstein, and really made it much broader, and he basically claimed that, you know, almost all particles, maybe all particles, have both a particle and a wave-like aspect, okay? The bigger the particle, the smaller the wavelength, so the harder to see the associated wave, but nevertheless this was a basic principle. Then Werner Heisenberg spectacularly came up with matrix mechanics to try to understand, you know, what's going on with these systems. Actually, there were a couple of sort of almost equivalent formulations of the dynamics of a quantum system. Also, Erwin Schrödinger came up with the Schrödinger equation, which is sort of the fundamental driver of how things evolve in the quantum world. And Heisenberg's matrix mechanics turned out to be sort of something roughly equivalent to that. And Paul Dirac, a British physicist who probably is the 20th century second greatest physicist after Albert Einstein, he also developed a sort of an equivalent algebraic version and sort of explained the equivalence of these various stories, and also come up with the first quantum field theory and many other things. And I'll just also mention briefly Heisenberg's uncertainty principle, which is also a sort of a key aspect to this. So there's a lot to this story, obviously, but I think that it's not so easy to explain it until we look at an example. And there's a sort of a canonical example that you find in every text and every explanation. And so we'll also have a look briefly at that too. Okay, so you don't really appreciate the weirdness of quantum mechanics until you've spent a few weeks, at least, thinking about the two-slit experiment, which is sort of the canonical weird thing that people observed. And that is still a conundrum. I mean, it's still absolutely remarkable and just baffles the mind, you know. Okay, what is a two-slit experiment? It's a relatively simple thing that you can do. In fact, you know, it's probably accessible at some level, even in a very rudimentary way. It involves a little beam of particles, maybe photons or even electrons. Doesn't really matter what the particles are. And you have a little piece of some surface here with two small slits in them, okay? Two little slits. And they're very close to each other. I picture them as reasonably far apart, but you should think of them as being really close to each other. And there's a screen behind this, this object, the two slits, okay? And we're shining our particles, having a beam of particles directed towards this thing. And some of them are going through these slits, and then they're showing up on the screen behind, okay? That's what happens. So the first thing that we might do is say, well, what happens if there's just one slit? Okay, so maybe we cover the rightmost slits. Now there's only this one slit. And we shine our beam on this slit. Well, what happens is that you're getting some images on the background screen. And somewhat obviously, sort of the area directly behind the slit ends up getting the most hits, okay? But there is some kind of diffraction that occurs, okay? So as you go a little bit further from the image directly behind the slit, there's still some more images. So you shine this light for a while and you count how many, blips or where the light ends up emerging on the screen. And you find some pattern like this, so some distribution which is reasonably sort of uniform going down. Okay, and the same thing happens if you do this thing with the other slit open. So there's the right slit open, and you get a similar kind of pattern. It's maybe a little bit shifted over, but not much. It'll still be the same. And now the interesting thing is what happens if you have both slits open and you shine this beam of light or electrons. Well, then what happens is that you get an interference pattern, just as if these things were waves. So maybe it's simpler to think of light. You just have a beam of light, okay? So we think of light as being waves, and it's a kind of a classical experiment that if you have some situation like this, the waves are going through and then they end up having some interference. So on the screen behind, you will have some bands of dark bands and light bands, dark bands, etc. And reflecting the interference and the superposition of these things, okay? So that's kind of almost a classical physics kind of experiment. But now the interesting thing is that you can slow down the intensity of this light. So you can dim the light by having fewer and fewer photons being emitted. In fact, what you can end up doing is you can end up slowing this thing so far down that you're basically just emitting single photons at a time. Now you might think, well, single photon, that's not going to be, you're not going to be able to see that. Well, in fact, the human eye, if you're a young person and you're in a really dark room, it's possible to actually see or register a single photon. So our eyes are pretty sensitive. So that's not impossible to see. So you just shine a single photon on this. Now, you're shining the photon in this direction towards these slits. You don't know which of the two slits it's going through, but you can still record where it ends up. You see a little blip, okay, and then you record where that blip was. And then you shine another photon and record where it was. And then you shine another photon and record where it was. And what you find is that this same interference pattern is preserved, even though you're just shining one photon at a time. So there will be bands in here, okay, like white here, that represent no hits. Even though if we just had one of them closed and there was a single slit and we just shot one photon at a time, we'd still get a pattern like this if we did many of them, okay, and just recorded where all the images were, we would find some gradual decrease as we go from behind the screen. But in this case, with two slits open, we seem to have some interference kind of behavior, even though we're only sending in one photon at a time. So that's telling us that this single photon, even though we're thinking of it as a particle, has a wave-like nature. It's like the wave is going somehow through both slits. Now it turns out that's not just happening though with photons, it's also happening with electrons. Okay, electrons are different. In fact, it's happening pretty well with any particle. It's just going to be a phenomena that you're going to see. That even if you have a particle that doesn't seem to have anything to do with light, and you shoot it at a two-slit thing like this, and you look to see what are the various possibilities behind, you're going to see interference. Okay, so that's pretty weird. But then, to make it even weirder, is what happens when you decide to try to determine which of the two slits this electron, say, is going through. Okay? Maybe you have some detectors just at the slits that register whether the electron is going through the right slit or the left slit. So it lights up. So it's just been green. That means we've known that the electron that's gone through there has just gone through the right slit. If we have these detectors in place and we can see left, right, left, then this interference pattern disappears. And we end up with just the same kind of pattern that we had in these cases here, even though the two slits are still open. So if there's a wave-like aspect, it can still do the wave-like thing, but somehow the presence of this detector has, physicists say, collapsed the wave function. Okay? So these days, physicists mostly think that this particle, even if it's an electron, has an associated wave, the wave function of the electron, which is like a wave, and it's somehow going through two slits. But if you observe it, if you make a measurement, then that wave function collapses and it becomes just like a particle, and you end up with a sort of an ordinary distribution like this. So explaining what's going on here has been a huge challenge for physicists, and all kinds of very different explanations have emerged. And maybe Feynman said something like, well, you know, that almost all of quantum mechanics is somehow encoded in this experiment. You can see all kinds of things in it. So that's really interesting. And so that's sort of like a starting point for trying to figure out quantum mechanics. But we'll see that on the mathematical side, there's other things that we can do, other things that we can look at, purely mathematical things, that also shed some light on the quantum story eventually. So this is an introduction to this series. We'll see where it goes, and we'll see if we can understand the mathematical side of this classical versus quantum dichotomy a little bit more thoroughly. I hope you'll join me for this adventure. Join up to become a member of the Wild Egg Mathematics Courses channel, and we'll do some quantum mathematics.